Hello everyone, my name is Danier, and I am a PhD student at Visual Information Laboratory at the University of Bristol. In this presentation, I am going to describe our work on texture-aware video frame interpolation. So the presentation is structured as follows. I am first going to introduce the background of the project, then our investigation on the effect of video texture on the performance of frame interpolation methods, and then I am going to describe our proposed method as well as our experiments. Finally, I will draw the conclusion. So what is video frame interpolation? It is a task of given two consecutive frames in a video, I0 and I1, to generate the non-existent intermediate frame, IT, where T is typically 0.5 for two-time upsampling. So it can be applied in many fields, for example, to upconvert the frame rate of a video for enhanced visual quality, also to generate slow motion videos such as this one, and it can also be applied to video compression. For example, work has been done on enhancing the motion estimation component of conventional video codecs, and also to enhance the error concealment performance at the decoder side. So what are the challenges of video frame interpolation? First of all, for high quality interpolation, it requires accurate modeling of the motion, which is difficult due to the variety of texture and motion patterns present in real-world videos. For example, fluids, like water, generally exhibit vastly different motion from motion exhibited by rigid objects, as can be seen in the animation. And even between the rigid objects, some texture would result in more complex motion. And there are also other challenging scenarios, for example, occlusion, abrupt brightness change, and large motion, etc. Existing solutions, typically state-of-the-art deep learning methods, generally can be categorized as optical flow-based and kernel-based. Whereas optical flow-based methods predicts the optical flow and uses flow information to warp the intermediate frame. The kernel-based methods predicts adaptive local kernels, that is to be convolved with input patches to synthesize the final output pixel. Throughout these methods, various components have been devised to handle occlusions, brightness changes, and large motions. However, few attempts have been made to discriminate between different video texture and exploit the different performance of the models on different textures and adapt the methods to the content. However, previous work on video texture analysis and synthesis have shown that it is beneficial generally to handle static and dynamic textures separately. Moreover, it was shown in previous work that texture can be classified using texture-relevant features as well as encoding statistics into three classes. The first class is called static, which involves rigid texture exhibiting perspective motion, for example, things like a moving car. The second category is called dynamic discrete. It represents textures with discernible parts undergoing perspective motion independently. For example, branches of a tree blowing in the wind. The third category is called dynamic continuous. It represents spatially irregular and unstructured texture moving as a continuum. For example, water, smoke, fire, etc. It is a natural question to ask that does the class of texture affect the performance of video frame interpolation methods? And while generalization is a desirable property for deep learning based models, is there benefit in adapting the models into different textures, i.e. to overfit texture? It is to ask also that would overfitting into specific texture be favored over a model that is trained to generalize to all types of texture? And these are the questions we are trying to answer in this paper. So to summarize our contributions, firstly, we investigate the impact of video texture type on the performance of state-of-the-art video frame interpolation models. Secondly, we will show through our experiments that it is generally harder to train a generic video frame interpolation method that performs well on all types of textures than to train separate models, each specializing in a specific texture type. Finally, we will propose a novel texture-aware frame interpolation framework called TAFE that can generalize to any frame interpolation method and improve its performance. So let's dive into our research. So first, we're going to present our results on the investigation of the effect of video texture on performance of VFI models. So we evaluate state-of-the-art VFI models on 3 types of texture to see if texture type has a significant impact on VFI performance. The test set we used is HomeText, which includes 120 videos with 250 frames each. The primary feature of HomeText dataset is that each video is homogeneous in texture. Each video contains only one of the 3 texture types. Specifically, there are 45, 50, and 25 videos labeled dynamic continuous, dynamic discrete, and static, respectively. The VFI models we adopted include Arakov, Kane, and GD Comdat, which are relatively recent models that achieve state-of-the-art performance. They all have source code and pre-trained models available. The results of our evaluation are shown in the box plot here. Looking at the one on the left, on y-axis we have PSNR scores, and on the x-axis we have different categories of video texture. 3 colors represent 3 different models. And the other 2 plots only differ in the metric represented in the y-axis. It is noticed here that the distribution of the scores obtained by the models vary with texture type. Specifically, all models achieve the highest PSNR, SSIM, and VMAP scores on static textures, which is expected since the perspective motion of the rigid objects is relatively easier to capture. For the case of dynamic texture, all models saw degraded performance, and the degradation is even more severe for dynamic continuous texture, which is expected because this type of texture exhibits the most irregular motion that is intrinsic to the scenes containing water, fire, and smoke, etc. And to assess whether the impact of texture on VFI performance is statistically significant, a one-way analysis of variance is performed with the results shown in this table here. Here we can see that in terms of all metrics, texture type has significant impact on performance of VFI models at p smaller than 0.05 level. To further distinguish between each 2 pair of textures, we also carried out t-tests between the performance of the models on each 2 pairs of textures. The results of the t-test is shown in this table here. Each entry in the table represents the results of a t-test, where each row compares 2 different textures. The last 2 rows of the table show that, in terms of all metrics, the average performance of the models on static textures is significantly superior than the performance on dynamic textures. And looking at the first row that compares between the 2 dynamic types, all models have significantly different SSIM and VMAP scores. Combining the results of the t-test and previous analysis of variance, we can confirm that texture type does have significant impact on the performance of VFI models at p smaller than 0.05 level. Having known that VFI models perform significantly differently on the 3 types of textures, we therefore propose the following framework. So given a VFI model, we train 3 different versions of it, each version exclusively trained on one type of texture only. And during inference time, because we're focusing on the performance on homogeneously textured videos, we know the texture of the test video, so we invoke the corresponding model according to the texture. This is as opposed to training a single generic model for all texture types. Next, I will present our experimental results. Firstly, a little bit of setup. So the datasets we used include HomeText for evaluation, which is described previously. And to train the models, ideally, we would use homogeneous sequences so that each model can be tuned to a single texture type. Therefore, we make use of the publicly available homogeneous texture video datasets, including DynText, BVI texture, and Syntex. In total, we obtained 214 dynamic continuous textures, textured videos, 222 videos that contain only dynamic discrete texture, and 110 static textured videos. Considering this relatively small size of our training set, we've decided to start the models from their pre-trained weights and then tune them separately for each texture for around 15,000 iterations. So, as a reference, each model also has an extra version that is tuned on a combination of 3 types of textures, denoted as mixed. And the evaluation metric we used are PSNR and SSIM, which are the most commonly used metrics in the literature of video frame interpolation. And our final results are summarized in this table here. Again, looking at Adakov first, we have 5 different versions of the model. Baseline means the pre-trained version provided by the author, and DINDIS static represents the 3 types versions of the model that are tuned to 3 different texture types, and the mixed represent um, the one that is tuned on the mixed texture. We show the results on the 3 subsets of home text as well as the overall home text dataset. The 3 subsets represent 3 different textures that are included in the home text database. Looking at Adakov model that is tuned to interpolate dynamic continuous textures, the resulting model achieved better performance with 0.46 PSNR gain on dynamic continuous texture, with degradation in performance on the other two texture types. Similarly, for the Adakov fine-tuned on dynamic discrete texture, it achieved better dynamic discrete performance on dynamic discrete datasets with degradation in other textures. And this is similar for static texture. At the same time, although the Adakov trained on the mixed texture also achieved some improvement on the dynamic textures, such improvement is not as high as those achieved by the specialized models. And it can be seen there is a degradation in performance of the mixed model on static textures, and we attribute this to the relatively small proportion of the static texture in our training set, which is approximately 25%. So in overall, we can see that the models overfit to a specific texture perform the best on that texture, and the combination of the models that overfits different textures will outperform the one model that is trained to interpolate all types of textures, as can be seen from the scores achieved by these models on the overall home text database. And the overall trend is similar for the other 2 models, Kane and JD-ConvNet. So what conclusions can we draw from this table? First of all, we have verified that video texture does have significant impact on the performance of VFI models through ANOVA tests and t-tests. And we have seen from the previous table that each model fine-tuned on a specific texture overfits that texture class and outperforms the model trained on a mixed texture, i.e. the separate models specialized in different textures outperform the single model trained to interpolate all kinds of textures, implying it is which is as expected because overfitting to a texture is generally easier to generalizing to all types of textures. And this also implies that our proposed method is effective in terms of improving the state-of-the-art VFI model's performance. So lastly, let's discuss some limitations of our work and some future work that's possible. So first of all, we only focused on inference on homogeneous videos, i.e. Each video in the test set only contained one type of texture instead of generally textured videos. Secondly, the optimality of the texture classification wasn't exploited. For example, the question of is 2 classes better than 3 is not answered in this paper. Thirdly, the evaluation metrics we adopted are PSNR and SSIM, and their perceptual optimality is still a research question in terms of video frame interpolation. Some of the future work include to develop a large-scale homogeneous video database so that the models can be trained from scratch to specialize in one type of texture. And secondly, we need to come up with a computationally efficient way of adapting to different textures. So instead of training 3 versions of the model, each tuned to a specific texture, we can add some kind of parameterization to the model so that it can adapt to the different texture. Right. It is acknowledged that the author is funded by the China Scholarship Council, University of Bristol Joint Scholarship, and these are the references that I use in this presentation. Thank you very much for listening.